Math 1314, Tyler Junior College, Section 2.2, more on functions and their graphs. In the two remaining videos, we're going to talk about a special type of function and then a special type of operation you can perform on a function. This one, piecewise functions, is a special kind of function. I affectionately call these Frankenstein functions. Why? Because to create them, you have to take a piece of one function and sew it or glue it to a piece of another function, and perhaps attach it to a piece of a third function. And there's no limit to how many functions you can glue together. There's only one stipulation. The function has to know what to do with each individual x value and can only do one thing with each individual x value. For example, let's take a look at this function. Suppose f of x equals the following mess. You can spot a piecewise function because there's usually a giant brace catching all these functions together as one entity. F of x equals 4 if x is less than or equal to -2. Actually, I'm going to change this first condition. If -7 is less than or equal to x, which is less than or equal to -2. I have my reasons. You'll see why in a moment. So f of x equals 4 if x is between -7 and 2, including both. But f of x equals x squared if x is between -2 and 3, not including either. And f of x equals -6x plus 27 if x is greater than or equal to 3. It's important in a piecewise function that these domains do not overlap, because if they did, for example, let's say this said -2 is less than or equal to x, then where do I put the -2? Because it satisfies both conditions, I would technically put it in both of them, and there's a possibility that they could come out different. In this case, they would come out the same. But usually they would come out different. And so your domains have to not overlap. Now here's how a piecewise function works. Imagine you're in a restaurant and you need to go to the restroom. And for the sake of a simplistic discussion, let's momentarily assume a binary gender, male and female. I'm not making a political statement, I'm just simplifying the example. Before you go into the door, you look at the sign on the door and decide which one you satisfy. If you're male, you go into this door. If you're female, you go into this door. Again, not making a political comment, just simplifying an example. A piecewise function is kind of like that. The x is going to go through a door, but it's got to figure out what door to go through. The doors are over here. So if I invented math, I would have written this before I wrote the functions. You have to look at the conditions on the x to decide which function to use. If your x satisfies this condition, this is the function you use. If it satisfies the next condition, you use this function. And if it satisfies the third condition, you use the third one. So you don't put the x in every function. You put it in one. But you have to make the decision based on the input and the conditions imposed on the x. For example, let's evaluate f of -5. The first thing we have to do is figure out which one of these conditions -5 makes true. So let's start at the top. Is -5 between -7 and -2? Yes. So for this one, since -7 is less than or equal to -5, which is less than or equal to -2, then we're going to use the top function. The top function is pretty easy. The top function says, I don't care what your input is, your output is 4. This is called a constant function that always produces the same output. So out comes the 4, because that's all the top function does. It says, give me something, I'll give you a 4 in exchange. But what about -2? Which of the 3 conditions does it satisfy? It also satisfies the top one because it says less than or equal to. Doesn't satisfy the second one because it doesn't say or equal to. So along the same reasoning, since -7 is less than or equal to -2, which is less than or equal to -2, we're going to use the top function. And again, the top function says give me an input, I don't care what it is, your output is 4. Well, what about f of 0? Which condition does 0 satisfy? Is 0 between -7 and -2? It is not. Is 0 between -2 and 3? It is. So, since -2 is less than 0 is less than 3, we're going to use the middle function, which says give me a number and I'll square it. So 0 squared is 0. And by the way, if you're wondering where these conditions came from, I made them up. In most examples, they will be made up for you, so you don't have to build this, you just have to use it. There are situations, though, where you have to build a piecewise function. Let's see, f of 1. Which condition does 1 satisfy? First, second, or third? It satisfies the second condition. 1 is between -2 and 3. You don't have to write these phrases in red. I'm just justifying why I'm using the function that I'm using. Since -2 is less than 1, which is less than 3, we're going to use the middle function, which says give me the input and I'll square it. 1 squared is equal to 1. The last two inputs, 3 and 4, satisfy the last condition. 3 is greater than or equal to 3. 4 is greater than or equal to 3. So, since 3 is greater than or equal to 3, and since 4 is greater than or equal to 3, then we'll use the bottom function on each. The bottom function says give me a number, I will multiply it times -6 and then add 27. -18 plus 27 is 9. And when I put in 4, I get -6 times 4 plus 27. -6 times 4 is -24 plus 7 is 3. So evaluating a piecewise function is an issue of first deciding on the door in which you're going into based on these conditions, which I wish they weren't at the end, I wish they were at the beginning. And then once you've decided which function to use based on the input and the conditions, use that function on the input. Now, this is a function, and we can graph it. But how do you graph a piecewise function? I'll show you how. There's a couple of ways to do it, but one way is to just graph each one of these, ignoring those restrictions on the domain. For example, if we graphed f of x equals 4 by itself, that means whatever the input is, the output is 4. So every point would be 4 up. So it would be this graph. That's f of x equals 4. Graph the middle one. F of x equals x squared. We know that. It's a parabola. It does this. As far as f of x equals -6x plus 27, we haven't analyzed linear functions completely. Some of you may already know that this has a slope of -6 and a y-intercept of 27. But I can tell you what it does is it starts really high and comes crashing down like that. Now, this collection of graphs can't possibly be a function because all three of them collectively fail the vertical line test everywhere. Because both of these graphs go left and right forever. So no matter where I drop a vertical line, all three would eventually hit it. So how do we get the piecewise function? We only keep the parts of the graph according to the conditions. For example, the first graph is only valid between x equals -2 and x equals -7. So if I go back to -7, this graph starts at -7. So we'll put a closed circle there. There's nothing to the left of -7 because my function doesn't know what to do with those numbers. So it starts there. And it ends at -2. Now here's where we have to be careful. Does it end before or after the parabola starts? In order to do that, we got to figure out where they cross. Well, they cross actually at -2. How do I know that? Because when I put -2 in the top function, it just comes out 4, but when I put -2 in the bottom function, it also comes out 4, which means the parabola and the horizontal line meet at -2, 4. By the way, this one over here is -7, 4. Now, the line is the graph between -7 and -2, not the parabola, so we lose that. Now, I didn't plot these points, but 0, 0 is here and 1, 1 is about there, but we should know that the parabola looks like that. So this is where the line ends, so I can get rid of the rest of the line. Okay? And now the parabola takes over until we get to 3, so we got to figure out where the parabola ends. Well, I can figure out where the parabola ends by putting in 3. Now, I know 3 is not part of the parabola here, but I need to know where it stops. 3 squared is 9, so the parabola ends at 9, which is actually, believe it or not, going to be right here, 3, 9. Now, it's not required that where one graph ends, the next one begins. I just designed this one that way. But as we go upwards, the parabola stops at 3, 9. Now, how do I know 3, 9 is also on the line? Because when I put 3 in the line, it came out 9. So the parabola ends here, so no more parabola, and the other line begins here. So this part of the line doesn't exist. I can check it by plotting 4, 3, which is about here somewhere. Now, if you're wondering about open and closed circles, normally the parabola would be graphed like that because it does not include the endpoints. But it just so happens that where this segment ended is where the parabola began. So this is filled in not because of the parabola, but because of the line segment on the left. And the same argument for this empty circle on the parabola there. Normally it would be empty, but the other line met it there and filled it in. It is possible for this line to say start way up there and there's a gap, or this one be lower and there's a gap. But again, this particular one was connected. And does this graph look familiar? It doesn't. Go back and watch video number 2.